Once you know how to write electron configurations for atoms, you then can determine whether they are paramagnetic or not. All right, paramagnetism is the effect where substances with unpaired electrons are attracted to a magnetic field. So if you put these substances in a magnetic field and they are paramagnetic, they will be attracted to that field. Okay, so that happens for substances with unpaired electrons. And if the electrons are paired up, then that effect will be canceled out. All right, so let's do a couple of examples. One is the carbon atom. The electron orbital box diagram type of configuration for it shows the electrons. You have two 1s electrons, two 2s electrons, and then two in the 2p, which are, because of Hund's rule, in two separate orbitals. All right, so you have two unpaired electrons, which are in that 2p orbital, and therefore carbon is paramagnetic because they have two unpaired electrons. Okay, so these two electrons make it be paramagnetic. Contrast that to neon. If you do the electron configuration for neon, it's got a filled 1s, a filled 2s, and a completely filled 2p. So there are no unpaired electrons. In other words, all the electrons are paired. So it is not paramagnetic, and the term when all the electrons are paired is diamagnetic. So neon is an example of a diamagnetic substance. And actually all of the noble gases then will be diamagnetic as long as they are in their ground states and following the Aufbau principle. So let's try some more examples. This one you should try for yourself. There's 4 different atoms here. Draw the orbital diagrams so you can see which electrons are paired or not and determine if they are paramagnetic. Alright, I'm going to assume that you have stopped the video and done that. The electron configuration for beryllium is helium 2s2, and since we've already determined that noble gases have no unpaired electrons, we know that the part in the brackets will not make it paramagnetic. It's only the part outside the brackets that we have to be concerned with. So if we look at a 2s orbital and you have 2 electrons in it, they pair up, and therefore beryllium is diamagnetic. Now let's look at nitrogen. Its electron configuration is helium 2s2, 2p3. So all we have to do is look at the 2p3, which is 3 orbitals with 3 electrons. Those are unpaired, therefore this is a paramagnetic substance. So nitrogen's paramagnetic. Then we can look at manganese. Okay, let's find manganese on the periodic table. Okay, it's over here. Oops, it's over here. So you can see that it's going to be argon and a 4s2, and then there are 5 electrons in the D. So the configuration will be argon, 4s2, 3d5. We only have to look at the 3d5. There's 5 electrons in it, so because of Hund's rule, they'll be all in separate orbitals. Therefore, it is paramagnetic. All right, finally, let's look at zinc. Let's go back to the periodic table. You can see zinc is here at the end of the 3D. So let's go back. We can write the configuration. It is argon core, 4s2, 3d10. So we just have to look at the final one, which is D. And since there are 10 electrons, it's going to fill them completely, so that's diamagnetic. Alright, so only nitrogen and manganese were paramagnetic. Alright, so now that we've determined that nitrogen and manganese are the only paramagnetic species of these four, we can also talk about comparing how paramagnetic they are. For in other words, we can say which is the most paramagnetic. Okay, and for that you look at how many unpaired electrons there are. For nitrogen, we found 3 unpaired electrons. For manganese, there were 5. Therefore, the most paramagnetic would be the manganese with the 5. Okay, we can also look at the electron configurations of ions. Ions are simply an addition or a subtraction of electrons to make a species charged. So we usually start with the neutral species and then change it to make it an ion. So for example, if we want to know the electron configuration of Cl-, we first look at the electron configuration of chlorine. So the chlorine configuration is written here already. Cl- means we've added 1 additional electron. So we simply put 1 more in, following the same principle, Aufbau principle, that has an electron put in the lowest available orbital. So the configuration for Cl-, chloride ion, is almost the same as the original, but the last orbital will get 1 more electron. So 3p5 becomes 3p6 for that additional electron. We can also make cations. If we want potassium cation, we start with potassium that's neutral, and we can use the noble gas configuration, which is argon 4s1. We're going to take away 1 electron for making it positive, and that one we'll take away is the one that's 4s1, because that is the last available electron. So it simply becomes the argon core for our electron configuration for K+. For selenium 2-, we're going to have to add 2 more electrons to the selenium configuration. Okay, selenium is argon 4s2, 3d10, 4p4. Those last 2 electrons will go in the 4p4, making it 4p6. All right, now there is another subtlety I need to tell you about. If you are in row 4 or higher and you're making a cation, there's a little bit different rule on where the electrons come out of. Okay, the electrons come from the highest n value, not the last orbital. And I'll show you what I mean by that. Okay, this is only for making positive ions. If you look at iron, if you want to make the Fe2+ or the Fe3+ configuration, look at neutral iron, just like we did before, which is argon 4s2, 3d6. Now, filling by Aufbau makes the 3d be the last orbital, but the highest n value is actually the 4s. Okay, so the highest n is 4s. When you take electrons out, you take out of the highest n value. Okay, this is a 3d, so that's n equals 3, and 4s, you actually take them out of the 4s. Okay, so to take out 2 electrons for Fe2+, you take out those 2 4s, and the configuration becomes argon 3d6, because the 2 4s electrons are gone. So again, back to the rule. In row 4 or more, the electrons come from the highest n, not from the last orbital that was filled. Now what if I need to take out a 3rd electron? Well, that will come out of the 3d6 because there's no more n equals 4 left. So Fe3+ is argon 3d5. Here's a couple of them for you to practice by stopping the video. The first one, P3-, again I like to write the neutral species. P, phosphorus, is neon, 3s2, that's a 2, 3p3, and if you're making it 3-, you're making 3 more electrons, so it's neon, 3s2, 3p6 for P3-. Alright, how about zirconium 2+? Let's look where zirconium is on the periodic table. It's in it's element 40, so it's going to be a krypton core and 5s2 and 4d2. So let's go back. So zirconium is krypton core 5s2 4d2. So if we're taking 2 electrons out, they're going to come out of the highest n. Which is 5. There's 4d, but that's an n equals 4. So then the configuration will become krypton, we took out 2 electrons, took out those 2, 4d2.